we present unsupervised model-based dense face alignment. In this work, we show how to train a network to estimate dense correspondence from a face image to a 3D face model without supervision, such as ground truth or landmarks. Firstly, we briefly introduce previous approaches of dense face alignment and 3D face reconstruction. In early works, neural network is trained to regress face representation such as face model parameters, correspondence, or 3D shape. As this approach requires ground truth data, it can be applied to only limited objects. To ease this limitation, supervised approach has been proposed. This approach optimizes convolutional neural network to minimize error between an input image and a generated image based on image formation model, so-called renderer. However, most of self-supervised approaches still rely on weak supervision such as landmarks, identity, or multiple frames, or has limited capability. Until now, a few self-supervised approaches have proposed the training of a network without annotated data. However, in self-supervised approach, a reconstructed face tends to shrink as the outer region of a face is difficult to explain by a face model. Furthermore, careful adjustment of parameterization are required for successful training, and this causes the lack of robustness against arbitrary in-plane transformation. To resolve these problems, we propose to combine self-supervised approach and correspondence estimation. We employ image-to-image CNN to estimate correspondence, and this brought various merits, including robustness against arbitrary in-plane transformation, as well as capability to introduce loss function to prevent face shrinking. The network runs from self-supervision provided by the linear model itself. We show how to use differentiable linear least squares to estimate geometry and camera parameters from the estimated correspondence, followed by lighting and albedo parameters. This is the architecture for training. A network estimates correspondence, depth, and confidence map from the input image. Based on the estimated correspondence, we warp 3D movable model on the input image. Then we calculate optimal camera parameters and shape coefficients as the closed-form linear least square solution. Next, we calculate optimal inverse lighting parameters and albedo coefficients. In this way, we reconstruct for geometric and photometric parameters from the correspondence in differentiable manner. During training, we minimize robust residuals of the least squares as well as reconstruction error between the input image and projected vertices. We also use statistical regularization and constraints for camera parameters to obtain a plausible result. Now we explain the technical detail of our approach. As a representation of a face, we use 3D movable model, which is commonly used for face reconstruction. For shape representation, position of each vertex is calculated as the sum of shape mean and the linear combination of shape bases. In the context of face reconstruction, we estimate shape coefficients from the input. For albedo representation, we calculate albedo on each vertex in the same way. The challenge in this approach is how to differentiably calculate face, lighting, and camera parameters from the output of the network. We warp 3D movable model on the input image by differential bilinear sampling of flattened 3D model based on correspondence. Then we formulate the problem as a linear system on each pixel and optimize it with differentiable pseudo-inverse matrix. Firstly, we calculate geometric parameters. Terms in the left side represent alignment of camera parameters to transform the depth map to the neutral pose. In order to make the problem linear, we assume full perspective camera model. Terms in the right side represent alignment of shape coefficient to the neutral pose depth map. We minimize the summation of the error on each pixel weighted by confidence value, as well as regularization term for stability. As this formulation is linear with respect to both camera parameters and shape coefficients, we can obtain closed-form solution differentiably. Based on the obtained geometry, we calculate photometric parameters. To make the problem linear, we introduce inverse spherical harmonic writing. In ordinary spherical harmonic writing is represented as a linear combination of spherical harmonic bases, and intensity of each pixel is represented as a product of albedo and lighting. This formulation is not linear, but bilinear with respect to spherical harmonic coefficients and albedo coefficients. So instead of lighting, we use spherical harmonic bases for inverse lighting. We empirically validate that inverse spherical harmonic lighting can reproduce common spherical harmonic lighting with enough accuracy as long as the lighting is moderate. Thanks to the inverse spherical harmonic lighting, we can calculate photometric parameters in differentiable manner. A term in the left side represents inverse lighting of the input image. The spherical harmonic bases are obtained from the estimated geometry. Terms in the right side represent the adjustment of albedo coefficient to the albedo of the input image. We minimize the summation of the error on each pixel weighted by confidence value as well as the regularization term for stability. As this formulation is linear with respect to both lighting coefficients and albedo coefficients, we can obtain closed-form solution differentiably. Next, we explain loss function. During training, we minimize robust residual loss, reconstruction loss, statistical regularization, and camera parameter regularization. Robust residual loss is the sum of residuals of both photometric and geometric least squares clumped by 1. Minimization of residuals has the effect to increase the pixels, which can be explained by the estimated model, and clumping shuttles an preferable effect from background and occluded pixels. We can observe low residual region expands and the face coverage is improved as training goes on. Reconstruction loss is the sum of errors between the input intensity and the reconstructed intensity over the projected vertices. We sample the intensity of the input image on each projected vertex by bilinear interpolation. Reconstructed intensity can be obtained by applying the inverse of the inverse lighting to the albedo of the reconstructed face model. We also introduce regularization terms. Statistical regularization is applied to the estimated 3D Mohr model coefficients to keep the result plausible. Camera parameter regularization is to keep the reconstructed intrinsic camera parameters within realistic values. The first term penalizes anisotropic magnification, and the second term penalizes shear transformation. Now we show our results. Our approach can train a network without supervision while avoiding shrinking effect. Utilization of an image-to-image network also improves the robustness against arbitrary 2D transformation. We compare our method with previous supervised and unsupervised approaches. Our method achieves rather face coverage and competitive reconstruction quality without using grand tooth or landmarks. We show some more additional results of reconstruction. As our approach only relies on the appearance of your face, and the representation is limited within 3D Mohr model subspace, it tends to fail in some cases, including extreme shadow, extreme expression, extreme pose, skin color background, and occlusion. In conclusion, we have presented the dense face alignment network can be trained with differentiable linear least squares without supervision. Utilization of image-to-image network enables face reconstruction under arbitrary imprint transformation, and robust residual loss enables ear-to-ear reconstruction. Thank you.